Hello. Um, I thought today do something a little bit different, seeing as I've had a bit of a break. What I want to do is just look at this problem here, because it's one of these problems you can easily find yourself waylaid and confused, and generally go down a rabbit hole, which doesn't help anyone. So what I'd like to do is look at this situation. So what have we got here? We've got a square. And we have these three lengths all coming from the edge of the square. And we'd like to know what its area is. So we've got a length of 4, length of 2, length of 5. How can we find the area of the square? Now, you might be tempted to do all kinds of wonderful things. You might say, right, well, here's my square. You might say, right, okay, so I know things. I know if I call that x and that x, Uh, and that's 4, 2, 5. Now I can do something with that angle there and that angle there. So call that theta, call that phi. I know that's x root 2. And then I can use cosine rule. You can see that actually get complicated very, very quickly. If you start involving cosines and cosines of angles, then you tend to end up with some rather unpleasant decimals. So what if we try a different track? Why do we try something a little bit more simple? This is what we're going to do. So more basic than trigonometry, or the most basic bit of trigonometry, it's Pythagoras. Still trigonometry technically. Trigonometry just means measuring triangles. So what I'm going to do is I'm going to create right angle triangles. Look at this. So let's be geometers and start giving things names. O, A, B, C, D, E, and F. Now, what I'd like to do is start giving things. So we've got 4, 2, and 5. Let's start involving some unknowns. So I'll call that X. So that means that's X as well. I'll call this Z. So that means that's X, and so we'll call that Y. And now we realise we've got 3 right-angled triangles that are in some way related. So we've got the first right-angled triangle is this one. That's O, A, oops, made a mess of that. O, A, F. What do we know? We've got 4 there, we've got Y there, and so we should know that this is the square root of 16 minus y squared by Pythagoras' theorem. What else have we got? We've got this triangle here, which is O, P, F. So that's 2 there, length y there, and so we know that this length here is 4 minus y squared by Pythagoras. I've got one more right-angled triangle. It's this one. These are all right-angled triangles. So this has a length of x plus y. Sorry, this is angle OEC. This is Z. This is 5. So what have we got? We've got 3 equations essentially. Because see, the point here is we don't just know the whole geometry of the thing is that we don't just know what Pythagoras is. We know there is some relationship. For example, CE and DF are equal in length, and that's equal to Z, so that uh, this is equal to Z. And we also know that this AF is equal to X plus Z. So here are our 3 triangles. Right, yeah. 3 triangles. They're giving us 3 equations. We know that 16 is equal to x plus z squared plus y squared. We know that 4 is equal to y squared plus z squared. We also know that 25 is equal to x plus y squared plus z squared. Okay, so let's just do a little bit of rearrangement and simplification. So those are our 3 equations. So first of all, we notice we've got 16 is equal to x squared plus 2xz plus z squared plus y squared. We have 25 equals x squared plus 2xy plus y squared plus z squared. And we know that 4 equals y squared plus z squared. Which is all rather good, because you see what we've got here. What have we got? We've got this, and that, all appearing in all 3 equations. And that's equal to 4. So we've got 16 equals x squared plus 2xz plus 4. And 25 equals x squared plus 2xy plus 4. And then we can rearrange a little bit more. But notice now, what have we got? We've got 2 equations where we can now isolate we've got 2 equations where we can now isolate z and y. What do we know? We know that xz from the first equation, xz is equal to 16 minus 4 is 12 minus x squared over 2, which tells us that z is equal to 12 minus x squared over 2x. That looks complicated. Doesn't matter at this moment. Same sort of thing. xy is equal to 20. So 25 minus 4 is 21. 21 minus x squared over 2 tells me that y is equal to 21 minus x squared over 2x. And you think, well, what's the point now? Well, what we've got now is we've now got y, x and y in terms of z. And so what do we know? We know that 4 is equal to z squared plus y squared. Well, that is 12 minus x squared over 2x, all squared, plus 21 minus x squared over 2x, all squared. At this point, you're thinking to yourself, this looks horrible. Actually, let's just do a little bit more, just do a little bit of simplification here. So I've got 12 minus x squared, all squared, over 4x squared, plus 21 minus x squared over 4x squared. And that's all squared, remember? So this is... Now, why is that important? This is important because going back to the nub of the problem is to find the area. We're not asked to find the side length, we're asked to find the area. And the area is x squared. It's x squared we have to find, not x. So this is what I'm going to do. At this point, I'm going to say to the right, let a equals x squared. And it's a we want to find. So we now know that 4 equals 12 minus a, all squared, plus 21 minus a, pull it out, all squared, all over 4a. Rearrange and expand. 4 times 4a is 16, so clearing the denominator gives us... Right, so we expand 12 minus a squared, well, that's 144, minus 24, 2 times 12 times a, plus a squared, plus 21 squared is 441. Remembering there's that uh, lovely little relationship. 12 squared is 144, 21 squared is 441. So one of those nice little, not quite coincidences of number theory there. So 2 times 21 times a is 42a plus a squared. And so what do we have? We have 144 plus 441. So what's that? So we have 5, 8, 5. Minus 66a plus 2a squared. And what do we do? So now we've almost got a quadratic equation. So 16, 60, minus 66 take away 16 is minus 82. Minus 82a plus the 585. There we've got a quadratic equation in a quadratic equation. Sorry, I just realised my writing keeps falling off the bottom of the screen. Let's bring that back up. Bring that up. Oops. There it is. So we're left with this quadratic equation, which in theory we can solve, and it shouldn't be too difficult. So, actually, this is you have to use the formula, doesn't it? So what do we do? So we do b squared, so a is equal to minus b plus or minus the square root of 82 squared minus 4 times 2 times 585 all over 4. Right, so that gives us A equals, right, now this is where it's going to get rather interesting. 82 plus or minus the square root of what? 2044 over 4. That was a bit gruesome, but it actually, well, it does simplify a little. Plus or minus the square root of 500, the 2 lots of 511 over 4. So, what's that? That's 41 plus or minus square root of 511 over 2. So there's two possible answers here. Because obviously 41 is going to be 41 squared is bigger than 511. So we've got here a very nice, we've got two possible solutions here. And that just goes to show that actually the diagram we've drawn, there are two possible ways of seeing it. Because if you now have, if you were to know that the point is somehow inside the square like that, 2, 4, and 5, then that's the bigger value. So that's 41 plus the square root of 511. So that's a surprising result. A surprising result of the geometry. So we've got 41 plus the square root of 511 is the area of that square. But for this situation, the area 41 minus root of 511 over 2. So the maths actually shows you that there is something, there are two values, there are two ways of, of representing a situation that the diagram doesn't always have. Which is why you can't always rely on diagrams in mathematics. Sometimes they will surprise you. Proof by diagram is very seldom accepted. Right, so we've actually got somewhere. We've managed to solve a problem using just Pythagoras. We could have got bogged down in some very complicated trigonometry, but instead we got rooted in some complicated algebra instead. And the trick we found really was not to look for the side length, but we remember what the question actually asked, and the question actually asked the area. And although the answer is not what I would call neat, it is nonetheless you can find it using the methods we know. And it gives us that surprising result that there are actually two configurations to begin with. I hope you found that interesting. It's a simple problem mathematically. It doesn't go into anything higher than basic algebra and Pythagoras. But nonetheless, it is most satisfying to see, I think. So take care of yourselves and see you soon.